All right, welcome. In this video, I just want to do a quick exercise on sort of identifying the loop invariant and then trying to prove it correct if we've identified it. And so for that, I've created this very simple function here. Maybe let's just take a moment here to go through the function and see what we do. So first of all, this function starts with an input of A. A here is a list or a sequence of, well, I guess I haven't really stated, but as we've been doing in this series of videos, I'm going to stick with integers. So let's assume these are integers. And then what I'm going to do is, at least the way this function works, is I've got some flag named false, which we're going to, or set false rather, that we're going to return at the end. And there's the possibility of setting it to be true inside this looping structure. And that's going to be the focus of our of this video, is one, identifying the loop invariant for this loop, and then proving it correct. So as I mentioned, we set our flag to be false to start out, and then as I mentioned, we have the opportunity to set it true. We set it true when, and that's the next bit that we're going to identify here. It looks like we set it true when AI is less than 0. So if we find a negative, it looks like here, if we find a negative, then we set the flag to be true. So hopefully our internal, little processors, our little internal compilers, maybe if we've got a little bit of practice as programmers and maybe algorithm designers, we already kind of see what's going on here with this loop, which is by starting out false, if we don't find any negative numbers, then we'll never hit this part, and at the end there we'll answer false. So that's only if we don't find any negative numbers. So it looks like what happens is this function is going to return true if it finds a negative number, and false if it doesn't, meaning if they're all positive or 0. Okay, so again, we can think of this function maybe as just a quick negative finder. It's going to check to see if there's negatives. Now again, this might be a simple subroutine that you might use in some other algorithm that you might use. Just filter out lists that don't satisfy this condition, that have only positives or 0. What we're using it for is obviously actually not really the purpose of this, but rather can we prove that true. Now, the reason I've sort of selected a simple one here is because we can put it through our internal compiler and we can sort of go, yeah, that kind of looks correct. But the other side of that is that because our internal compiler has already sort of convinced us, yeah, this is correct, sometimes we can sort of be caught in this trap where we say, well, it's correct because it's correct. Sort of duh, or it's trivial, or clearly. And these words, we sometimes use them in our language or when we're trying to convince someone, but they really don't carry a lot of weight. When we say it's trivial, or we say clearly, or we say duh, what we're really trying to say is, well, fill in the blank yourself. Fill it in yourself. And that's not really what we want to do here. What we want to do is fill in the blank ourselves. We want to fill in the blank. So what that means is we need to start identifying here. So the first bit is maybe identifying what is the loop invariant. Now, part of the reason why I put this through our brain compiler already and jumped ahead and said, well, what does this whole function do? It detects negatives, is that gives us an idea of the finish line, where we're trying to get to. Okay, we know that ultimately if this function is supposed to detect negatives, if we want to prove it correct, say, then we want to at the end be able to say, well, if there's a negative in the list, it returns true, and if there's not a negative in the list, if it's all positives or zeros, we return false. And that's hopefully something that we can argue based off of the loop invariant that we've identified. So let's put some effort into trying to identify the correct loop invariant. In this loop, what's going on? One of the things we've got is our flag. Something about the flag is important, right? If at the end we want to say we return true or we return false given a certain situation, well, the thing that we return at the end here is this flag, right? And this flag is set in our loop or outside our loop. So something about how our flag gets set is going to be critical and important in our proof probably, and in our loop invariant itself, in the proposition, how we express it. Okay, but just the flag itself is not enough. So here I'm going to come up with a couple loop invariants after iteration I of the loop. Remember, this is sort of the clause or the phrase that we're going to use to start out our expression. And this expression might be multi-part. We might actually want to express this in a couple different ways. And in fact, maybe I'll start out here. I'm going to start out with an incorrect one that maybe I've seen. It's not necessarily incorrect. It's true, but it's kind of trivial. So let me show you. So remember I said something about our flag here. Well, maybe we might say flag is false or the flag is true. That's true, right? This seems to be right. After iteration I of the loop, the flag is either false or the flag is true. Now what is good about this and what is wrong about this? What is good about this is, yes, this is actually a loop invariant. And when I say this, I say a loop invariant. Remember, a loop invariant is any property that remains true after an iteration of the loop. Is it true after the iteration of the loop that the flag is false or true? Yes, that was actually true no matter what. This is a Boolean flag. We assume it's going to either be true or false, so it's always going to be true or false. That's the only values that a Boolean flag could ever be. So this is trivially true. So this happens to be true, but it's not going to help us. Remember, our purpose, our proof, is that we want to show that at the end, the flag will be true under a certain circumstance. And because we've left out that bit, we've left out what the circumstance is, this invariant that we've got, or that we've sort of partially identified here, is not necessarily what we want, but it's partial. So let's see if we can flesh it out a little bit more. What we really want to do here is we want to say, what is our flag meant to represent? It's meant to tell us something about the list. Okay, and again, we might jump at the end. What was it supposed to say at the end? If we answered true, then it was because we had found a negative, right? So we might want to say here, the flag is true. When will the flag be true? The flag will only be true if we found a negative. And I'm going to add in a clause here that I tend to use in a lot of my loop invariant because I think it's important to how we think about the loop invariant, which is the clause so far. So far, okay? At the end of the loop, at the end, when we return our flag, it's true if we've found a negative in the whole list. But after iteration I of the loop, the flag will be true only if we found a negative so far, and that's the important bit here, so far. And what does that mean? That means up to the current element that we're looking at, in this case AI. Okay, so let's see if we can express that again. We were down here in this bit. So we had flag equals true, and what does that mean? That means we found a negative, okay? And so we might say, and AJ. I'm going to use J here. Why did I use J? Why not I? Well, the reason is I'm already using I over here, and I is showing up here, and I is showing up here. I means something already. I means the iteration that I'm currently in. Now, what I want to say about J is that I want to say two things about J, but just to finish my point here, one thing I want to say about J is that it's in this set. It's in the set so far. Now, remember, so far, that looks like the total set that we've got, except the last element is going to be AI instead of AN. This is what's making us get the so far clause in there. Okay, the AI is standing in and saying so far. So what have I got so far here? I've got flag is equal to true and AI is part of this set so far. That's not all we wanted to say though. Sorry, I said AI, but I meant AJ. AJ is out of the set so far, okay? And we wanted to say something about AJ is that when we encountered AJ, it was a negative. So we might want to add that part on there as well. And AJ was a negative. Okay, another thing we can do here, and I noticed I had a few students that use this sort of notation, that they referred to this set, if we have this set up here, A, as being the whole thing, they referred to sort of this subset as A, or subsequence to be precise, as AI. And if you use this subset, again, I said subset again, I mean subsequence to be very precise, but this subsequence sort of notation, then it simplifies the things that you have to write down below. If you said this was AI, so you might write this, I've got put this arrow, of course that's not the right way to do it. If we wrote this properly, we might do AI is equal to in here instead, something like that. Or we could define it up ahead above our theorem if we wanted to as well. But using that kind of notation will simplify down below. When we want to write it down below, we can just write AI instead of this long sequence. And then also this notation allows us to talk about other subsets like AN, which is the whole thing, right? Or, as we'll see in a bit, we'll probably want to talk about AI plus 1. And now we've got just a real easy way to write it. We could write it up here too by putting a plus 1 in there. But this is just a nice easy way to write that too. So if you have the idea of using that notation too, that's a pretty good one. Okay. We only finished the part 2 here. What about part 1? When is the flag false? Well, I'm going to be a little bit of a cheater here for a second. One thing we could do is we could swap the order of these two, and I could just say, well, it's false otherwise. It's false in all the other cases. Okay, so we could say here the flag is true if we've found a negative, or it's false otherwise. Okay, meaning we haven't found a negative. So the other thing we could do here is we could take, now why did I say swap these two here? Well, the otherwise clause usually is conditional on some first clause, so we usually have to put that second. But we could also state explicitly what we mean by otherwise here by using the same kind of notation and format that we did over here. Okay, so we might say here that what do we want to say? In this case, it says we found some negative, while the other way of saying that is all of those elements are positive. So we might say AJ is greater than or equal to 0. Remember, we had the possibility of being equal to 0 here for all. And then we could use the same phrase here if we wanted. We could say, but now I'm going to use the shorthand that we introduced, because now that we have it, it's might as well, right? For all, oops, I put AJ here, let's put AI. So that could be cashing out our otherwise phrase here. Of course, we need an and to join them up here, but and all of our elements are greater than or equal to 0 for all the elements so far. Remember, this is still capturing that so far clause. Okay, all of this is good in how we might piece this together, but there's another way we can capture this, and it sort of captures this idea of the otherwise, is basically we're tying together two conditions. We're tying together what happens when our flag is true and what it's telling us about this list AI. So I'm going to just rewrite this whole thing in a slightly different way just to show us how we can write it a little bit more concisely and precisely. So here I've got one expression which I think takes advantage of natural English a little bit. Here we're saying after iteration I of the loop, the flag is false, or, and this expression here is what we just used for we found a negative so far. Okay, and I've just expressed it again with a couple different, let's go through the notation choices to make sure. I use J instead of I because we've already got I over here. I've used that AI notation so I can use it again down below, right? I've really just said this. And I've just said it's a negative number, okay? So we found an AJ that's negative so far, all right? Now what this is taking advantage of is this or, and it's making use of the, remember there's an ambiguity in ors, but this is making us think, or it's stressing, usually when we emphasize it in this type of way, we're stressing that we mean exclusive or, meaning not both. So we might sometimes do this, not both as an extra clause just to remind ourselves here, okay? And what this means is one of these sides of this dilemma is true, not both, okay? Now, why is this one way that we can, this is sort of a natural English way to express this, but if we wanted to express this again in logic ease, we might change this from false to true, and then instead of using this or, which remember I'm saying is an XOR, an exclusive OR, okay, we could change that out for an if and only if. Now, why is that? Well, that's because an if and only if is equal to a not an XOR, okay? So by flipping this from a true to a false and from flipping the XOR to an if and only if, we get something that is equivalent or also true. So that would be saying the flag is true if and only if, or only under the conditions that we found a negative so far. So all of these are actually the initial one we phrased, the one with the XOR, or the expression with the if and only if. All of these are the same way of sort of expressing the same clauses. Which one is correct? They're all correct. Which one is best, again, is sort of dependent on what your purpose is and what your style is. Okay, so everyone's got a different style. So let's see if we can try and prove this. And let's remember, we're going to do this by induction on usually the same iterator we're using over here on I. Now we usually use a base case where we start before the loop. So in this case, that's going to be I equals 0 is what we usually use. So we know I is never actually set to 0, but that's just an expression of before the loop. So we'll say before the loop, what do we know? We know that flag is false. Now, some of us might go ahead and say, well, that's all I have to prove then, because it just says flag is false or this. Well, actually, there's a little bit smuggled in there because of the not both, okay? Because we said not both, that just because the flag is false, that means we also have to show that this is not true then, okay? We've got that this is true, then this part has to be not true, all right? So let's go ahead and say that. So we've got the first part, flag is false, and so let's see, what is it that we need to show? AJ is an element of, sorry, remember, we have to show this is not true. So that means, remember, this clause over here meant that we had found a negative so far. So if this has got to be not true, that means we have not found a negative so far. So another way of saying that is all of the numbers are positives or zeros. Okay, well, let's see, first of all, let's see what that list is. That list here is AI, which is A0. So we might say AI is A0, which in this case is just the empty sequence. And, well, there are no zeros, or sorry, there are no negatives. So there are no elements. Oops, I put an element sign there. I meant, oh, I guess I think I tried to do a less than equal to, and it just looked like an element of sign. So let's be more precise here. Oh, and I didn't want that. I wanted completely less than. So let's make sure it's right. And that's the important part about these proofs, of course, is we want to make sure that we get them correct. Which I will say this, which is one reason why I'm making this video, it's helpful. I'm sort of, after I write this sentence, I reread it out because I want you to, listen and hear in. And as I read it out, my brain checked it and said, oh wait, that's not exactly what I meant. And so it might be helpful for you when you're writing your own proofs to sort of do this. I find I've got myself into my own habit, but go read what you just wrote again. Did it make sense? Maybe it didn't. Maybe you messed up. A less than equal to was supposed to be a less than. Maybe your I was supposed to be a J. Okay. So again, let's read this through and let's see if this makes sense. So before the loop, the flag is false, and we wanted to show that this was not true. So we went and we looked and we said, well, what was our AI? Our AI was empty. So that means there are no negatives in the empty sequence. Of course, that's easy. Okay. So that part is done. So let's move on to our inductive hypothesis. So there are a couple ways to set up your inductive hypothesis. Now the way I do it usually with my loop invariants like this is I say, well, assume what happened prior to iteration I plus 1. I've changed my I to I plus 1 here because whatever happened after iteration I is probably what's happening prior to iteration I plus 1. So I can usually just copy the rest of the clause down here down. Okay, so I might put this here. Flag is equal to false, or, and remember that's an XOR, or we've found a negative. And here I'm using the shorthand so I don't have to keep writing out that. That's the whole point of using the shorthand, right? So I don't have to keep writing that out. So I've got my AJ, I found some AJ, this is the so far part, and this is the negative part. Okay, I found a negative so far. So assume prior to getting here, prior to getting into this iteration, that we've found that our flag is either false or we found a negative so far. So I'm going to continue down here with my inductive step. Okay, so in the inductive step, we usually start by saying, well, what is it that we even need to prove? Well, we've got it stated up here, okay, that the flag is false or we found something so far. The only thing we need to change here is that so far now includes iteration I plus 1. So we need to prove that the flag is false. That's the same as above. Or, and the only bit I've changed here is my I to my I plus 1, saying that now that we've included iteration I plus 1, that if we find a negative, it must be so far up to and including the new element now, AI plus 1. Okay, now how we split these up now, how we attack this bit, is really up to us. And ultimately there are 4 cases. It depends on what happened when we came in. When we came in, was it false or had we already found a negative? It depends, right? Also, then what happens in this step when we've got here AI plus 1 technically, because we're in iteration I plus 1. But what happens? Is this number a negative or not? That determines what's going to happen in this step. Now, how we attack these 4 cases, if we just write each one down and attack them one at a time, that's kind of a brute force approach, we're good. We can do that, okay? But it turns out actually that we might be able to lump some of those cases together so that we don't have to tackle them all at the same time. Okay, and so the way I'm going to do that is I'm going to point out, this is just the way I'm thinking about it. You might think about it a different way. You might want to tackle all 4, but I'm going to do case 1. I'm going to start with case 1, which is prior to iteration I plus 1, either the flag is false or this is true. So I'm going to assume this is true. I'm going to assume AJ is in AI and it's negative. So why did I tackle this case first, and why do I think I might want to be lumping some of those cases together? Now remember, this is the case, so I said the 2 cases were what happened coming in and then what happened on this line here. Well, coming in, we're saying that we've already found a negative number up till so far. If we've already found a negative so far, then flag will already be true based on what our hypothesis is. And we know that in this step, even if we found another one, the flag would still be true. Okay, and we never change the flag back to false, or there's no chance in the loop here to change it to false. So once it's true, it's already true. It will stay true and remain true. And so that makes this bit somewhat trivial. It's not completely trivial because I just said what it was that we needed to argue, okay, which is, and another way of seeing this is maybe looking at this, is we could say, since AJ is in AI, so since we've found a negative so far, and AI is just equal to, now I need to be a little bit careful here. I'm tempted to use subset notation or set notation, but we have a sequence here, not a set. So I was tempted to say something like AI is a subset of AI plus 1. That sounds like what I mean. I'm going to be clearer. Okay. Here, actually, what I'm talking about is I want to say what AI plus 1 is. So again, talking it out loud helped me realize that I need my notation right here. But what is AI plus 1? It is AI concatenated. I'm going to use the concatenation symbol here. Although there might be other symbols for other notations, but I'm going to use concatenation here to this one, AI plus 1, taking that element and adding this one on. So I'll go back to this notation here. Oops, that shouldn't be an S, that should be an A. AJ is an element of AI plus 1. Okay. So basically, I'm trying to make a very formal argument here saying that this negative number that we have already found in AI, since AI is included in AI plus 1, it must also be in I plus 1. So we're done. Okay, so we know that AJ is an AI plus 1, and maybe I'll just add the last bit to make it very clear, and AJ is a negative. We know that. Okay, that was part of my case assumption. So what I've done in case 1 here is I've taken this simple, not necessarily trivial, but fairly simple case and lumped two cases together. It didn't matter if the number we were looking at here was another negative or not. We are already in the case where we're going to return true. So let's look at the other case here. The other case here then would be flag is equal to false. And if the flag is equal to false, and here maybe because this was the way I stated it, but it's going to be important here. Remember that if flag is false, then this other clause here has to be not true. Okay, so and AJ is greater or equal to 0 for AJ in AI. So again, while we were leaving this unstated, allowing sort of our internal logical processors to just carry it along sort of implicitly, it's now going to be important, so I'm going to make it explicit by writing it out. Okay. Now it is going to matter what happens in this stage, because at the end of this stage, the flag might still be false. Or at the end of this stage, I keep saying stage, how about iteration, because that's what I really mean. At the end of this iteration, the flag might still be false, or it might have switched to true, depending on this line. And so we should probably put that into two subcases. So what should be my first subcase? I might say AI plus 1 is greater than or equal to 0, because that's the same case that I've got here. Okay. All of these elements are greater than 0. So now we might conclude, so we might say AJ is greater than or equal to 0 for all the AJs in AI plus 1 now. Okay, you basically just following the same logic we did right here, saying that since we already knew AJ were positive or zeros for all of them so far. We've confirmed for the next one that it is also a positive or a 0, so therefore we can extend our so far from I to I plus 1. And that's really what we're doing in the inductive step, is trying to extend that so far clause from I to I plus 1. So let's look at our next subcase. Okay, and this is sort of, again, where some of the key logic is going to come in. We're looking at this case and we're saying, hey, AI plus 1 is less than 0, right? And AI plus 1 that's the check we're doing exactly on this line. So we know now that the flag is going to be true, okay? But when the flag is true, so we've turned this part off, okay? So in this case, since the flag is now switched to true, we now need to verify that this bit is true. Okay, verify that this bit is true, of course extending our so far now to being I plus 1. So how do we know that that part is true? Well, it's because this is the one. Since aj, which we can say is equal to ai plus 1, is less than 0, and aj is in ai plus 1, we basically confirmed the second condition. I'll just add, again, maybe I'll put this in brackets since I had it in brackets up here, the extra bit, and flag equals true. Okay, I just wanted to finish that clause here. I guess I put a little equals, or a period there at the end there. But since I had a since there, I'm just going to add that and finish that clause by saying our invariant holds. Another thing we could have done is maybe just eliminated the since, because really what we've got here is we've just got the clause we were looking for right here. That clause is what we're looking for because that's what we had stated up above. Okay, it's what's stated here, sorry, in our inductive hypothesis, and it's what's stated above where we've already stepped back. Now I just want to finish it off by completing the proof with what I usually call as the postamble, where we might just say by induction, after iteration, I of the loop, the flag then is going to be equal to false, which is one of our conditions, of course, or remember we mean that as XOR. And now our condition about saying finding a negative so far. And so maybe I'll just phrase that again. AJ is greater than 0. That's not right. It should be less than 0. And AJ is an element of AI. And we're done. Okay, so that was intended to just be another quick exercise, an example of how to identify a loop invariant. And then prove it correct using induction. So I mentioned in this video that there was maybe 2 or 3 different correct ways that we could have phrased this loop invariant, and each way we would phrase it comes with sort of different approach in our induction. Although the logic behind the scenes, the steps that we're making behind the scenes are usually all the same. So what those differences are then is your style, and as I've mentioned maybe a couple times now, we all have our own style, and it's fine for us to develop our own style. You don't need to have the same style as mine, and that's one of the reasons why I wanted to show you more than one way that we could characterize this loop invariant. All right, thanks a lot for watching, and we'll see you in the next video.